All right, welcome to Geometry, Unit 1, Lesson 13. It should be, what is it? It's going to be February 13th. It's going to be a Wednesday. We're almost halfway through the week. All right, we got that long vacation coming up. Let's look at this. Well, I'm gonna cough already. Oh, pausing the. I was able to rescue you from that cough. Learning target today is that I want you to be able to say, I can use visual structure to identify transformations of polygons using rigid motions. So I want you to be able to use the structure, the visual structure that you see, to be able to identify transformations. Remember, those transformations are rotation, going around. We have reflection, things flipping over. And we have translation, which is things moving around. They might move anywhere along, all right? So rotation, reflection, translation. These are all transformations, and they're all called rigid motions. They're rigid motions because the shape doesn't change, the size doesn't change, angles don't change, sides don't change. What can change is orientation. Rotation changes the orientation, how something's rotated. The reflection can change how it's flipped. It can be like a mirror image of itself. And the translation just moves around. It doesn't change orientation nor it being flipped, all right? So here's a little riddle I want you to solve. Some of you will just count these, but there's an easier way, and I want you to see the shortcut. We have here an interesting little shape. How many shaded triangles are there in this polygon? All right, how many shaded triangles are there in this polygon? You might be tempted to count them out. You can, of course, but there's an easier way. Find the shortcut. Go. Pausing the video here. All right, unpausing the video. So some of you might have started counting along the row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, you might have done that. However, if you began to see the visual structure of this, you might say, oh, I noticed that it's a hexagon. I notice it has 6 sides. 6-sided polygon is a hexagon. And I noticed that, so there's inside this hexagon, there are these equilateral triangles. There are how many equilateral triangles inside the hexagon? There's 1, 2, 3, 4, 5, and 6. So there's 6 equilateral triangles inside this hexagon. And each of these triangles in the hexagon have the same number of shaded triangles inside them. So I can just count 1, 2, 3, 4, 5, 6. So there are 6 shaded triangles in each of my smaller equilateral triangles here. And there are 6 of them. So times 6 triangles. What's 6 times 6? Someone shout it out for me. Yes, of course, that's 36. Or you could have counted them all out, There's sometimes with math, there's shortcuts. There's easier ways to figure things out. A little application of the old noggin there. All right. So what do I want you to do right here is this is called an little activity I call spot the transformation. All right. I want you to circle the correct word which describes how the first shape has been transformed to the second shape in just one transformation. So I want you to think about how the first shape here, all these shapes have been transformed here. Like let me do the first 3, okay? I'm looking at this and I'm saying, okay, this got turned. It got rotated. See, it was like this, and now its orientation has changed. This one, I have a small diamond. I got a bigger diamond. We haven't talked about this yet. We're going to get into it later. It's called a dilation. Dilation is when something gets bigger or smaller, a dilation. This has obviously gotten bigger, so we say this has been enlarged. It hasn't been flipped that I can tell, and it hasn't been rotated that I can tell, so I'm done there. And then this one, okay, I'm looking at this shape. I'm thinking it looks the same size. Hasn't been enlarged, reduced, but it has been rotated. It doesn't look like it's been flipped, not that I can tell. All right, you do the next ones. Pause the video here. Okay, unpausing the video then. All right, I'm just looking at these. So this one has been flipped. You can see it's a mirror image of itself. This one's been rotated. As we see, that's that upside down. If I took this triangle, I turned it upside down here. that would be rotated. This hexagon here has been reduced. I'm about to cough. Pausing. Saved by the pause button. And this shape here has been flipped. It's a mirror image of itself. Give me that smiley face reflection as to how you feel about this. Was this an easy activity? Hopefully it was. I'm hoping that was pretty cool. All right, now we got to talk about rigid motions. We need some definitions here. We're going to talk about all our different motions. All right, sorry. Magic of video here. So a rigid motion. A rigid motion is a transformation that preserves distance. It's a transformation, it's change that preserves distance, which means after we do a rigid motion, if you think, what does rigid mean? Anyone know? Shout it out. Uh-oh. Sorry, that little bell was a household announcement. Maybe I can edit that out in post-production. But that probably take too much work, so I'll just keep going. So a rigid motion, it preserves distance. So if the pre-image, the thing I have before, the triangle I start with, and the triangle I have afterwards are going to be exactly congruent after a rigid transformation. What are rigid transformations? Rotations. Everything stays the same distance, same angle, same everything. Reflection stays. Everything stays the same size. All the angles stay the same. The triangles are still congruent even after they're reflected. And then translation. Triangles are just shifted position, shifted where they are on the grid. They haven't changed at all. However, we looked at a new transformation called dilation. Dilation is not a rigid motion. Dilation changes the size, so it's not a rigid motion. Did anyone say what rigid was? Rigid means unmoving, unwielding, doesn't resists pressure. Rigid, like a wrench is rigid, right? All right, translation. A translation is a rigid motion that slides every point in the pre-image in the same direction and by the same distance. So let's write that out. All right, through the magic of video editing, I've written out to translate what I just said. Hold on, I'm going to cough. All right, so a translation is a rigid motion that slides. That's the word I want you to associate with a translation, is slides. A translation is a rigid motion that slides every point in the pre-image. All the points in my initial triangle just get slide over to another point on the graphing paper, all right? So that's a translation. Slides every point in the pre-image in the same direction, in the same distance. Again, it doesn't change shape, doesn't change size. It's just going to be translated over somewhere else. It could go up and down or down and to the left. You can translate things all over the place. Reflection. We've done these. Hopefully, I know some of you, quite a few of you liked these. All right, so there's actually two different kinds of reflection. So far, right now, we're only concerned with what's called a line reflection, when we reflect over the y-axis, like we've seen before in previous lessons. When we reflect over, say, the y equals 2 line or something like that. It's a line reflection. So we're reflecting over a line. I'll also show you another kind of reflection later. It's called a point reflection. We're going to reflect over a point. Those are kind of neat. They often look a lot like a 180-degree rotation, actually. So, but we're going to get concerned with line reflection. So a line reflection, or reflection that we're looking for, is a rigid motion in which every point has a mirrored point. So when you think of reflection, I want you to think mirrored. All right, I want you to think of that line of reflection as a mirror. That reflected image has a mirrored point on the other side. All right, so rotation now. All right, so rotation now. Wheels rotate, right? A rigid motion, what I want you to remember for rigid motion is spins, all right? Spins. Rotations spin. So it's going to be, a rotation is a rigid motion in which every point is spun or spins by a fixed angle around a center point. So if you're doing a rotation, you need a center point. Oftentimes it's the origin, 0, 0, but it can be any point really. And then that image is going to be spun around that point. That center of that rotation is going to be the center of the wheel in which everything's going to be rotated by a certain degree angle. We've done some 180-degree rotations. We can do 90-degree rotations. We can do 10-degree rotations. We'll show you all those in the future. Right now, just rotation. It spins around. The shape spins around. And then dilation is the new one we've learned today. All right, so the exact technical definition of dilation gets a little funky. We could say it's a similarity transformation about a center point, such that O maps the pre-image P to image P prime, such that O, P, and P prime are collinear, and all sorts of stuff like that. We could do that, or how about we just say, for the sake of what we're doing in this class, dilation makes a figure bigger or smaller, right? Dilation makes a figure bigger or smaller. And usually when we talk about dilation, we talk about our eyes. Our eyes can dilate. When you go into a dark room, the part of your eye expands. It opens up to let more light in, so you can see better in the dark. If you go out on a sunny day when the sun's out, your iris is going to constrict. The dilation is going to go smaller to let in as little light as possible, so you're not blinded by the bright light. So there's this idea of this iris dilates open and closed as your eye needs to be able to see in the conditions that it's in. All right, insert eye dilation part of the video here. Magic of video. Okay, hopefully that was cool. Let's see. Now what I want you to do, well, I just want you to look here. So let's talk about these bicycle images here. I have a bicycle that's going to get translated. Notice how the front of the bike is still here. The front of the bike is here. When I translate this bike, the image just goes to a different place. Okay. Now actually, I know technically I've moved all of these bicycles. They're all been translated in a way. But what I wanted to get the idea is that a translation doesn't change orientation. It doesn't change size. It just changes location. Okay, translation. Now let's look at reflection. Notice when this bike is reflected, and this is actually a point reflection, over a point somewhere here, this bicycle got turned upside down and backwards. It's now a mirror image of what it was. Right? Here's my pre-image. There's my image. That's what it was before. That's what it is now. It's upside down and in the other direction as it was. This is a point reflection. We'll show you some more of those point reflections. They're pretty neat. All right, now we have rotation here. Rotation. What's the difference? Well, it's not backwards like here, right? But it is upside down. Why is it upside down? Because the bicycle's been rotated 180 degrees. It's been turned. It's been spun. Right? So the orientation has changed, but it hasn't been reflected. So that's a rotation. And last but not least, we have our dilation. Do you see how that has been dilated to be small? It's almost, if I had to guess, a 1/4 dilation. It's been shrunk to 1/4 of its original size. Looks less than half. Now it might be a half dilation. I have to measure. If I took a measurement of this as a ratio of measurement of that, I could figure out what kind of dilation this exactly was. That's what we have. Translation, moving around from location. Reflection, flipping a mirror image. Rotation, changing orientation, spinning around a center. And dilation, getting bigger or smaller. All right, let's change the page. We are 13 minutes in. Oh my gosh. We're moving too fast. We're going to get done early today. Yay! Don't party too hard now. All right. Triangle ABC has vertices -1, 1. -1 work. Okay, so -1, I have to go back on my x-axis, back 1, up 1. So there's point A. B is at 1, 3, where x is 1, y is 3. Where x is 1, to the right 1, up 3. 1, 2, 3. There's B. And C, where x is 4, y is 1. Where x is 4, 1, 2, 3, 4, y is 1 right there. So this is my triangle that I have. I'll put a C there. This is what we call the pre-image. This is the image I have to start with. All right, do we see that all right? There we go, okay. The image of triangle ABC is going to now be after a transformation. Now we have this notation. I know it's really hard to see on this, probably on this camera, but hopefully you can see it okay on your paper. If you're really squint, I'm going to need to figure out a way to expand some of these. Hold on, I'm going to cough. All right. So it says, after the transformation, we have a little r, a y equals x. So the little r means reflection, and it means reflect over the equation y equals x. What is the equation y equals x? So if I just make this bigger, it's lowercase r, y equals x. All right. What is that? This is actually a linear equation. It's the simplest linear equation that we can do. What it says is that for whatever x is, then y. So it says that if x is 1, y is 1. If x is 2, y is 2. All right? So it's saying the slope here is 1 over 1, right? Up 1 over 1. And it has no constant there, so the constant is going to be 0. So we're going to start at the origin. Our constant is 0. We start at the origin. And we're going to go up 1 over 1. Up 1 over 1. Up 1 over 1. Continue to go up 1 over. It's just a diagonal. Kitty corner to all these squares here. Right? There is my y equals x line. All right? Now I have to reflect my shape over this line. So now I have to look, okay. This point here is going to go perpendicular. Remember, perpendicular is 90 degrees with this right here. So this is my new point across that line. It'd be nice if I did it in a different color probably. Try blue. Here's my B. I've got to go across this line, down 1 over 1, down 1 over 1. There's my new B. And C, to get to this line perpendicularly, I have to go up 1 over 1, up 1 over, up a half over a half. So up a half over a half, up 1 over 1. So this is my C prime. C prime here. B prime here. And A prime here. I know this is probably kind of small. I hope everyone can see what I'm doing. Here's my new triangle. After a line reflection. Now notice that this reflection changed the orientation. The triangle's still the same size as it used to be, but it's been turned 90 degrees. Does anyone have any ideas on why reflecting over this particular line would change the rotation of the line by 90 degrees? Anyone got any ideas on that? Pause the video, and we'll see. And unpausing the video. And maybe you're thinking, okay, hopefully we realize it has something to do about this diagonal line. Because this diagonal line is halfway between here and here, and this is 90 degrees. By reflecting along a line that is halfway between it, we're going to turn it, the reflection actually turns the shape 90 degrees. Not upside down, but just 90, perpendicular. Because it's halfway itself between 90. So that's what happens there. All right, very good. We are only 19 minutes into the video, and let's see, how much more do we even have to go? Let's look through our thing. Not much to do today. We have one more thing to do, and then the check for understanding. All right, here it is. In the diagram below, triangle ABC, ABC, there's triangle ABC. See that triangle ABC there? And triangle XYZ are graphed. What we have to do is use the properties of rigid motion to explain why triangle ABC is congruent to XYZ. All right, I'm going to let you think about this. What rigid motions could we use to transform ABC into XYZ that would show that it's congruent? Can you find a rotation, a reflection, a translation that would do this? Pause the video here, work for a couple minutes. Let's see your magic at work. Come on, let's put our brains together here. All right, hopefully we cooperated a little bit in class and we talked this out, and there is some thoughts on this. So as I'm looking at this, I'm noticing that this is up, down 1 over 1, down 1 over 1. So to go from C to Z, I did either a point reflection or a rotation. One of the two. I did one of those. Either I reflected over this point, or I rotated C 180 degrees. One of those two things went down. Could be either or. A, I'm noticing to get from A to my center, I go down 1, 2, 3, 4, left 1. So down 4, left 1. And then to get to my next point, which A would be corresponding to, I would go left 1 and go down 4. 1, 2, 3, 4. There's X. A and X are corresponding points. And this would also be either a point reflection or a 180 degree rotation. Does that make sense? And then B, I have to go down 1 and then to the left 1, 2, 3, 4, 5. Down 1, left 5. And then down 1, left 1, 2, 3, 4, 5 to get to Y. So I can tell that since all three of these points, I can rotate them 180 degrees. I can say capital R, rotate triangle A, B, C, 180 degrees. That's a terrible 8. 180 degrees. We could also say reflect and 0, 0, triangle A, B, C. Actually, let me reverse this over here. Let's rotate 180 degrees. Rotate 180 degrees. Triangle A, B, C. So either one of those, can you see that? Capital R is rotate. That's the notation in geometry for rotation. 180 degrees, triangle ABC, and that'll be congruent with triangle XYZ. And then or a point reflection, lowercase r, over the point 0, 0, my origin up here. I'm doing a point reflection. If I was doing a point reflection, here's my lowercase r over this point, triangle ABC is congruent, triangle X, Y, and Z. That's what it is. All right, give me that smiley face. Reflection on this page. I want to see if this was easy, if this was too hard. How are we doing? All right, I am pretty much planning on leaving you to your own devices on this check for understanding. I want to get us towards independence on the check for understanding. But I will explain the directions at least. In this regular hexagon, A, B, C, D, E, F, shown below, AD, this whole piece right here, this whole piece AD, BE, this whole piece right here, BE, and CF, all intersect at G right at this point, okay? When triangle ABG, when this triangle here, put it in green, when ABG is reflected over BG, put put that in blue. Let that triangle is reflected over line BG, and then rotate it 180 degrees around point G. ABG is mapped onto, and you pick which triangle you think it's mapped onto after those two rigid motions, after that reflection and then rotation of 180 degrees. Hopefully we do all right on this. Give it some thought. Give it some time. Think about it. Puzzle it out. After you're done with that, give me reflection. A learning reflection, like paying attention to rigid motions, is helpful in presentation because it lets me know if things are congruent, right? Something like that. And then this reflection here, how's it working? How's the video? How's the class being managed? How are we doing? How are you doing? Let me know. Take all the time you need. Pause the video here. Okay, unpausing. Moving on to the homework. You know what? I'm going to let you do the homework on your own. It's multiple choice. It's, I wouldn't say it's easy. It takes some thinking. It might take you a whole minute or two. Apply your mind here. You can do this. All right? I think that's a wrap. Have a great day.